Auzubillahiminash-shaytanir-rajim. Bismillahir-rahmanir-rahim. This is lecture number 30. Analysis of the dispersion relation. In the last lecture we have studied the dispersion curves, Lamb mode spectrum, in which we have seen that we have dispersion curves corresponding to the dispersion relation, which is given here equation number 1, and we have seen that we have infinitely many Lamb modes for this equation number 1. All are asymptotically approach to CT, transverse wave velocity, and only one mode cross the line CT and approaches to CR, Rayleigh wave speed, and there is a plateau region in the spectrum of these modes. So normal behavior and anomalous behavior, we have discussed here that which type of mode has normal behavior and which type of mode has anomalous behavior. Anomalous behavior in the sense of the change in the sign of the slope. Today we will see some analytical proofs that when RC is less than CT, then we have only one mode which approaches to Rayleigh wave speed CR, and infinitely many modes intersect the line CL, and we have infinitely many modes between CL and CT. Let us start. We know that for equation number 1, in which we have, this is the special relation for isotopic plate symmetric modes. For symmetric modes, this is equation number 1. For symmetric modes, where P square is this and Q square is this, we have this omega is equal to kc. K is wave number, this is frequency, this is phase velocity. Let U is equal to hk. Now h is the thickness of the plate and k is the wave number. So when you take U is equal to hk, it means that we have normalized the wave number k. So using this, we can write this thing as P square h square U square alpha square, where alpha square is this, and Q square h square is equal to U square beta square, where beta square is this. Then we can write equation number 1 in the following form, which is in this equation number 2, where we have alpha and beta, and we have reduced U. What is U? U is normalized wave number. So case 1, when RC is less than CT, less than CL. No, we have alpha square this. So this is less than 1. From here we can see that C over CL less than 1. So we can take minus outside and inside we have 1 minus C square over CR square. So we have written this gamma square. So we have alpha square is equal to minus gamma square. It would be alpha is equal to plus minus iota gamma, and beta square is this. So this can be written as this. Beta square is equal to minus delta square, and delta square is this. So beta is plus minus iota delta. Use this in equation number 2. We have this and this and this. So when our U is very large, wave number is very large, then we can see that we have is there hyperbolic. So for large domain argument x, we have tan hyperbolic x approximately equal to 1. So for large U, we can write this 1. So this can be written as here, more over this can be written here. So this is the Rayleigh wave equation. This equation gives the value of CR, value of Rayleigh wave speed CR. So So it means that for this domain, our C is approaches to CR, and we know that this is the unique value for the Rayleigh speed is unique. So we can have this type of result. U is along x-axis normalized wave speed, wave number, and this is the normalized phase speed, and this is the lowest mode which crosses this CT and approaches this CR. That we have seen that there is C which approaches to CR. So this will approach to this CR, and we are between 0 and CT. So that is why this mode is below this line and approaches to CR because of this equation, that it will give us value of CR, Rayleigh wave speed. So when your wave number is very, very small, then what we have from equation number 2, we will use this thing, equation number 2. When wave number is very, very small, we know that for small u, tan u is approximately equals to u. So we can write equation number 2 in this way. So we have this thing. When you will solve this thing, you will have this value of C by CT. That this is kappa CL by CT. That when u is very, very small, then your value of phase speed is this one, and you need to obtain this from here. By solving this equation, you have to obtain this. Now when our C is equal to CL, that we have our C is equal to longitudinal wave speed CL, then in this case your alpha is 0, because alpha is equal to C square, or alpha square is equal to C square or CL minus 1. When C is equal to CL, so 1 minus 1 equals to 0. So equation number 2 can be written in. So when you use this thing, equation number 2, then you can satisfy your equation number 2 with this u. So again you have to solve equation number 2 by using this, and must have this value, this u. So this is telling us that we have infinitely many solutions, that we have infinitely many values of u when C is equal to CL. And also, in other words, that there are infinitely many modes which intersect the line C is equal to CL. It means this is the line CL, this is CT, and we know that when C is equal to CL, we have many u's, U1, U2, U3, U4 up to so on. It means that mode will cross this line at U1, this mode at U2, this mode at U3, this mode at U4. So we have infinitely many modes which intersect this line C is equal to CL, as I have said here. By changing value of n will be 1, u is equal to pi over k square minus 1 kappa. What is kappa? Kappa is material cost, and so you can have the value of u with the help of this. When C is equal to CL, 2 pi, 3 pi, 4 pi, you have different values of u, infinitely many values of u, because here you have infinitely many n's. Now when your C is between CT and CL, when your C is between CT and CL, now it means that our phase speed C is greater than transverse wave speed and less than longitudinal wave speed. So in this case, our alpha is minus gamma square. So alpha is plus minus iota gamma, and beta remains positive. Why? Because alpha contains C by Cl which is less than 1 and beta contains C by Ct which is greater than 1. So no effect on beta, so one radical is imaginary, so we can write this thing as alpha. For alpha this, so use this in equation number 2. We have this. As for large u, we can write this approximately equal to 1 and this can be written here, and when you use beta value of u, beta gamma, you can have this. So this equation has the property that for one value of u, for every value of c, between Cl and Ct, as in this case we are taking C between Cl and Ct, so for each value of C between Cl and Ct we have infinitely many values of this u, which is wave number, because we know that there are two unknowns, one is C and one is u. Ct and Cl, they are known. Cl is longitudinal wave speed and Ct is transverse wave speed. So for each value of C we have infinitely many values of u, because here we have 10, so we will have infinitely many values of u when our C is between Ct and Cl. So it means that when we have, for every value of C we have infinitely many solution, many value of u, so it means that we will have infinitely many solution for every value of C in this domain. So it means that when we have infinitely many values of u or infinitely many solution between this, so we have infinitely many modes in this domain. In this domain that we have infinitely many modes in this domain. And also one thing keep in mind, that Lamb modes, all these dispersion curves, they will never intersect with each other, that they will never cross with each other, that you cannot have two modes which crosses each other. So if it is so, it means that you have done some mistakes in the derivation of dispersion relation, or by plotting the dispersion relation something is wrong if they intersect with each other. So they will never intersect with each other. So we have infinitely many modes between Ct and Cl, and so it means that we will have infinitely modes between Cl and Ct. So from here we can, what we will say, that we can say that any line which is greater than Ct can never be asymptote to any of the mode. With the help of this result which we have seen here, what we have said for this result, we have said that we have infinitely many modes between Ct and Cl. So from there we are saying that there is no line above Ct, either it is Cl or between Cl and Ct or above Cl. There is no line above Ct and there is no line which can be an asymptote to any of the mode. Let us suppose that and this conclusion is including this line C is equal to CL, that CL can never be asymptote to any of the mode. There is a result that along the value of CL we can see that a slope of the mode approaching to 0. Slope of the modes approaching to 0, but modes can never be approached to CL. Their slope is approaching to 0 when C is approaching to CL. So in this case we said that that particular region is plateau region. That is the definition of the plateau region, that slope of the mode approaching to 0 at C is equal to CL. Now here we are saying that no line above CT can be an asymptote to any of the mode. Suppose that nth mode, any mode which is nth mode did have C1 as the limiting speed. So what does this mean? This means that here should be C dash instead of C1 we have C dash. So mistakenly I have written 1, so here would be C dash, this one, C dash. We are saying that we have a mode and we are saying that this is nth mode. This is approaching to a line C dash, and where C dash is greater than CT, that we are admitting that this C dash is asymptote to the mode which is nth mode. If this is so, then this we can show this here. This is CT, this is CL, this is any C1, and this is crossing CL and approaching to this C1. This is nth mode. So it means that we will have n-1 modes before this nth mode, and they will be between C1 and CT, because we cannot do that. We cannot say that any mode n+1 mode after this nth mode and cross this line CL again C1 and approaches to CT, because if this is so, then n+1th mode will intersect this nth mode, so which is not possible. That I have said that modes will never intersect with each other. This is the property of the modes. They will never intersect with each other. So it means that we have n-1 modes before this, and we have said that nth mode is asymptotically approaching to C dash. So it means that here will be n-1 mode between C1 and CT. If this is so, then it means that the value of C between C1 and CT, any value here between CN and CT, C1 and CT, will give us a finite number of solutions, which will be n-1, because that line will intersect n-1 modes, and at the point they intersect you can draw that u0, u1, u2, u3 up to un-1. So you will have n-1 solutions for this equation for the value of C between C1 and CT. But this is a contradiction. Why this is a contradiction? Because we have said that any value of C between this will correspond to infinitely many solutions of this equation But if we suppose that C dash is asymptote to any mode C, say nth mode, then we have a finite number of solution of this above the above equation for the C between C1 and Ct, which is a contradiction about the existence of infinitely many solutions for every C when C lies in this. So it means that no line above Ct can be an asymptote to any of the mode. So Ct itself will be asymptote to all the modes, because we have seen that only one mode will cross this Ct, and that approaches to Cr, Rayleigh wave speed. Now this is the spectrum which I have already shown you in your previous lecture, figure number 2.1 and 2.2, by using the dispersion relation for an isotropic plate, where we have written that which type of material we are using, and we have given the material value of material constant and value of Cl and Ct. In that figure you can see very clearly that there is plateau region along this value Cl, and all the modes are approaching to this value Ct, and there is only one mode which crosses this line Ct and it approaches to value Cr, Rayleigh wave speed. This is S0. S0 means that we have, S means symmetric mode, 0 means zeroth mode, first mode, second, third, fourth, fifth. This S0 sometimes called lowest mode. So along y-axis we have normalized phase velocity, and along x-axis we have normalized wave number. And this is the Rayleigh mode spectrum corresponding to equation number 1. Now you have to study the paper shape of dispersion curves for Rayleigh spectrum. This is the title of that paper, written by Professor Faiz Ahmed. So download that paper and read that one, solve that paper and obtain the results which are given there. All the some of the results I have discussed here, and some I have left for you. So you have to do that paper. Thank you so much. Allah Hafiz.